Right, so Bismillah ar-Rahman ar-Rahim. The chapter that we are going to study today, it's called Chemical Equilibrium. Equilibrium. Right, so this is a chapter which is quite in resemblance to A levels. So those of you who are from A levels will find this easy. All right, and inter में भी ये काफी अच्छे से पढ़ाया जाता है, so inter students will also find it fun. Now let's get started. Now let's look at the term's meaning. Equilibrium. So equilibrium means this is actually something which is equal on both the sides. Equal actually is from the word equal, and equal means it's balanced on both the sides, right? What are the two sides that we're talking about? It's actually the two sides of a chemical reaction that we're talking about. So a chemical reaction which is reversible and is in equilibrium, all right? Meaning a chemical reaction, if I have two reactants reacting with each other to give you two products, C and D, this reaction that I have written over here is a straight irreversible reaction, right? This is an irreversible reaction in which the reactants combine together to give you products and the reaction is finished. It stops and that's it. In reversible reactions, there's a second category of reactions. It's called reversible reactions, in which the reactants are continuously forming products and the products are continuously breaking down back into the reactants, right? If A and B combine together, they'll form the product C and D, but somehow C and D combine again to give you the two reactants back. Now, this reaction that I have written over here is a reversible reaction. Right, this is a very special type of reaction. It's called a reversible reaction. Reversible reaction. There is a forward arrow, forward half arrow, I should say, which represents the forward reaction, and a backward half arrow. These are two half arrows, right? This is a half arrow. You can call it a half arrow. All right. So half arrow will tell you about one of the two reactions which are taking place over here. All right, there's a forward reaction and a backward reaction. You can also call it right-hand side and left-hand side reactions. All right. Now, if the rate of this forward reaction, now this upward arrow, the upper arrow is representing the direction of the forward reaction, and the down arrow or the bottom arrow is representing the direction of the backward reaction. This is a backward reaction. All right, when the rate of forward reaction equals the rate of backward reaction, rate of the reverse reaction, in that case, this condition is known as, what is it known as? Anyone? It starts out with D. What is it called? It's called
dynamic equilibrium.
Yes, dynamic equilibrium. Right? So when the rates of forward and backward reactions in a reversible reaction are equal, we call it a dynamic equilibrium has been established. All right, we call it a dynamic equilibrium. So now this is the broad concept of a chemical equilibrium. All right, so chemical equilibrium can exist only in reversible reactions and not in irreversible reactions, because irreversible reactions, they form products and the reaction is stopped over there. All right, the products are highly stable in this case. They're highly stable, so they cannot break down back into the reactants. But over here, the products are also not very stable. They're less stable. They're comparatively less stable than the products of the irreversible reaction. So if they are less stable, then that means they won't stay in their original format for long. Rather, they'll quickly react together and form something else. This is what stability refers to. Okay, so this was a broad concept of a reversible reaction. Now, there are two classical examples of reversible reactions that we studied in our course. The very first one is the manufacture of ammonia or ammonia synthesis. The reaction by which ammonia is synthesized is known as the, what is it called?
Haber's process.
Yes. It's manufactured using the Haber's process, in which nitrogen combines with hydrogen forming ammonia in a reversible reaction. All right, if you balance it, this is the balancing. This is a gas, this is a gas, and this is also a gas. The conditions that are required over here is iron catalyst at a temperature of 450 degrees Celsius and a pressure of approximately 200 atmospheres. Okay, 200 atmospheres is the pressure, or this is a very high pressure. So just, you can also write down high pressure. These are the conditions which are important. They have been tested quite frequently as well. This is Haber process. This is a reversible reaction. It can be, it can go both ways. It can go forward as well as backwards. Take it. Now the rate of forward and backward reactions, if they become equal, then we'll call it a dynamic equilibrium. All right. We'll say that the dynamic equilibrium has been achieved over here. Catalyst. What is the role of a catalyst? Catalyst now. In case of a reversible reaction, this is a very crucial point to note over here. Catalyst role in a reversible reaction. Catalyst has, it does not favor any of the two reactions indiscriminately. Rather, catalyst, it favors both the reactions equally. Favors both the forward and the backward reactions. You guys know that catalysts, they actually speed up the rate of the reaction, right? So favors both the forward and backward reactions. So if the catalyst, it favors both the reactions, if it speeds up both the reactions, then that means it helps this chemical reaction to achieve its dynamic state or dynamic equilibrium more quickly. All right. So helps the reaction to achieve dynamic equilibrium more quickly. And it does not shift the position of equilibrium. All right, it does not shift the position of equilibrium. I'll explain what I mean by that. But before I move on, tell me everything so far. Is it clear? Is everything right? So now what will happen next? Now what will happen when the dynamic equilibrium is established? The rates of forward and backward reactions become equal. Well, it's common sense that neither the amount of reactants nor the amount of products would change after the dynamic equilibrium is established. So at dynamic equilibrium, the amount of reactants and products would become constant, okay? Amount will become constant, but not necessarily equal, okay? Do you guys understand this difference? Not necessarily equal. Okay, they may or may not be equal in amount, but they will become constant. Whatever their value is, they'll stay at that particular value. All right. So now let me represent the dynamic equilibrium using a graph. Now you've got the concentration of the reactants or the products on the y-axis against time. All right. And now initially, you know that the reactants would be at their certain concentration. All right. For example, this is the concentration of the reactants. And products initially would be 0, right? Before the reaction started out. Now we've got these two reactants only. Now we provide these two reactants with the right conditions and we set this reaction into motion and you start getting the products. And this is a reversible reaction. Now, as time passes by, the concentration of the reactants will fall and the concentration of the products will rise, correct? Because the reactants would start converting into products. Now, this will continue, right? The reactants would continue falling until they'll reach a constant value. The products would also continue rising until they reach a constant concentration. Now, the blue line represents the products, the red line represents the reactants. Now, I'm going to label this graph at 4 different points, and you guys have to identify the point after which the dynamic equilibrium has been established, right? So this is an imaginary dotted line after which concentrations have become constant, all right? So now this is a point. Let me just count it, point A, all right? This is point B, this intersecting point. This is point C and this is point D. Now tell me at which point is the dynamic equilibrium already established? That's the question. At what point is the dynamic equilibrium established in this graph? Any suggestions?
Sir, at point A.
Okay, any other answers? Anyone else? You've got one answer, point A. Ahmed, Fatma, आप दोनों को क्या लगता है? डायनामिक इक्विलिब्रियम किस पॉइंट पे अचीव हो चुका है? पॉइंट बी पे इन दोनों की कॉन्सेंट्रेशन बाय द वे इक्वल है. पॉइंट डी पे सिर्फ ये तो सी और डी तो नहीं हो सकते बिल्कुल भी. इट्स आइदर ए और बी. सी डी तो इसलिए नहीं हो सकते बिकॉज द कॉन्सेंट्रेशन
सर ए पे रीच हो चुका है. ए पे रीच हो चुका है.
ठीक है. ए. All right, so A is the unified answer and A is actually the correct answer. Good. Yes, it is A because at A, both the product and the reactants have become constant. ठीक है. Actually, इस dotted line के immediately बाद ही जो है वो dynamic equilibrium established हो चुका है. Okay, so yes, the point which is at dynamic equilibrium. ठीक है. Good. All right. Now, के बाद भी हो गया, आगे बढ़ते हैं. Now, there are a few laws. बल्कि नहीं, few नहीं, एक ही law है, वो हमें पढ़ना है. Law of mass action. किसको पढ़ लेते हैं? This is a very simple law, right? Total 2 मिनट में हो जाएगा. Law of mass action. पूछा जाता है तो इसलिए ये करा देते हैं. And this, I've seen a lot of MCQs being asked on this law. Right, so what is law of mass action? Law of mass action actually tells it's a law of rates of a reaction, right? It tells you about the rate of a reaction. It tells you that the rate of a reaction is proportional. It is dependent. The rate of a reaction is directly proportional to the product of active masses of the reactants. Now, let me explain what I've written. So rate of a reaction, according to law of mass action, is dependent or directly proportional to the product, means multiplication of the active masses of the reactants. So now let me tell you the meaning of active masses. Active masses actually means concentration of the reactants. So the law of mass action actually links the rate of a reaction and the concentration of the reactants. Get it? It tells you that the greater the concentration of the reactants, the greater would be the law of mass action. The greater would be the rate of the reaction. Okay, so if this is A combining with B, giving you C and D, all right, let me just make this a reversible reaction because it's the reversible reaction that we're talking about over here. And in this case, the rate of this reaction, the forward one, will be dependent on the product of the concentration of the two reactants, in the concentration of A into concentration of B. They're being multiplied. Okay. Get it, guys? And it again is common sense, because the greater the concentration, the greater would be the amount of frequent collisions between the reactant particles. And if there are more successful collisions and more frequent collisions between the reactant particles, then that would mean more products would be formed. Correct? All right. So the greater the frequency of collisions between the reactants, the greater would be the amount of products that you get. All right. So I'm going to quickly read through this paragraph over here, so in case we missed something. A state of dynamic equilibrium helps to determine the composition of reactant substances and the products at equilibrium. Okay, so we use a relationship derived by Goldberg and Wage in 1864. These are the two scientists' names, right? They gave the law of mass action. It states that the rate of a reaction is proportional to the product of the active masses of the reactants. Okay. Now the term active mass represents the concentration, and this concentration specifically is in mole per dm cube. All right, meaning the molarity. This concentration in mole per dm cube is also known as the molarity. Okay, mole per dm cube is also symbolized as capital M. I hope you guys know all of this stuff, right? Capital M, मोल पर डीएम क्यूब की जगह आप कैपिटल एम भी देखेंगे कई जगहों पे लिखा हुआ होगा. ठीक है. Now consider, okay, ठीक है. So this law of mass action has actually been used to derive an expression for another rate constant. All right, so let's quickly derive it. All right, this is very simple. Now over here, just look at law of mass action. It is talking about the reactant particles, right? We've got a forward reaction and we've got a reverse reaction, correct? For the forward reactions, the reactants are A and B, and for the reverse reactions, the reactants are C and D, correct? So if the forward reaction, if we just talk about the forward reaction, this is the relationship that we get. If we remove the proportionality sign, we will have to put an equal to and a constant. This is the equal to and the constant. Let's just call it KF, all right? Constant of the forward reaction into concentration of A into concentration of B, correct? Then let's make a similar equation for the reverse reaction as well, right? For the reverse reaction, rate is going to be proportional to the concentration of C and D, right? Because C and D are going to be the reactants. If we remove the proportionality sign, we'll need to put an equal to and a constant, correct? The constant for the reverse reaction is, let's just call it Kr into C and D, right? Now, what if this reaction is at dynamic equilibrium? This chemical reaction is at dynamic equilibrium. In that case, the forward and backward reactions are equal, right? So Kf into A into B equal Kr into C into D, correct? Now, Let's just take the ratios of the two constants. So Kf upon Kr equals concentration of the products divided by the concentration of the reactants. Correct? Now, these two constants collectively have a special name. They are known as, because we are dealing with concentrations only, they're collectively called Kc, or equilibrium constant of concentration. And the formula is products concentrations divided by the reactants concentration. And let me just add in something. They are to the power of their moles as well. But for now, let's just not bring that in here. Yeah, so this is the expression for Kc that we get over here. Now, let me tell you what this Kc stands for. Kc is the equilibrium constant. It's an equilibrium constant for concentration. And let me tell you what it means. Basically, if you have two reactants, A combining with B, giving you two products C and D, and I ask you to give me the expression for Kc for this reactant or for this reaction, Kc is going to be the concentration of the products to the power of their moles divided by concentration of reactants to the power of their moles. Now, let's say A is a mole, B, C, and D. These are the coefficients in this equation over here. Coefficients are actually the moles as well, right? So product is C, correct? So concentration of the capital C to the power of its mole to the power of the small c into concentration of the other product, which is D, to the power of its mole, which is small d, divided by concentration of the two reactants, concentration of A to the power of A into concentration of B to the power of small b. Okay? This expression that you have over here is the expression for Kc. Now, Kc actually tells you the position of equilibrium. If Kc is more than 1, what does it tell you? Kc being more than 1 would mean there are more products than the reactants. So equilibrium is shifted on the right-hand side. If Kc is less than 1, equilibrium shifted to the left-hand side. And if Kc equals 1, then that means concentration of reactants equals concentration of products. Kc being equal to 1 also means that it's at dynamic equilibrium. Well, that's not necessarily true, by the way. It may or may not be at dynamic equilibrium, but Kc being equal to 1 actually means that the reactant and the product concentrations have cancelled out. So they are roughly equal on both the sides. Okay? But they may not be at dynamic equilibrium. सही? So guys, ये बताएं Kc की expression समझ आ गई सबको? What Kc is and how do you write it down? If it's clear, please tell me. Please show me a raise of hand if it's clear. Expression for Kc. Ahmad, Mishle, आप दोनों को समझ आई?
Yes, sir.
ठीक है. So what's going to be the expression for Kc of this equation? Can someone tell me? What should I write in the numerator and in the denominator?
Sir, small c.
Small c?
Capital C, I think, and
Listen. It's a concentration of this capital C, right? To the power of the small c.
That's capital D.
Yeah.
yes, and capital D and the power of small d.
Okay, this coefficient,
Upon capital A plus capital B.
yes, capital A and capital B, and capital A to the power of the small a and capital B to the power of small b.
Their coefficient is Achha, sorry, never mind. I got it. Never mind.
Okay, so let me just give you another example. This is just a made-up example over here. If I ask you to give me the expression of Kc for this equation over here, although it's not for usually written for ammonia, but this is just a made-up example. So how are you going to write it down?
Yes, sir. NH3 square.
NH3 to the power of 2, okay, to the power of its coefficient divided by reactant
H2
hydrogen to the power of 1 multiplied by hydrogen to the power of 3. So yeah,
Okay.
this is how you write down the expression for Kc. Now, once you know how to write down the equation for Kc, you should also know how to write down the how to calculate the units of Kc, or units of any equilibrium constant. It's just like the unit of the rate constant. Now, in case of this one, this equation, the units are going to be the unit for concentration of ammonia in mole per dm cube. It's going to be mole per dm cube squared, right? Divided by concentration of nitrogen is again mole per dm cube, multiplied by concentration of hydrogen, again mole per dm cube, but this time it's cubed, right? So now what will happen is, okay, Nietzsche, it's in the numerator, you've got mole per dm cube, which is squared, and in the denominator, it's to the 4th power, right? The power is 4. So the square will cancel out and 4 will subtract 2 from it, right? So it's going to become 1 upon mole per dm cube, and this mole per dm cube is squared as well. So let's just simplify it. It's going to become mole to the power of -2, dm to the power of 3 to the, it's -6, so +6. So mole to the power of -2, dm 6. These are going to be the units for this Kc. ठीक है? Right. So ये तो बात हुई Kc की थोड़ी सी. आगे चलते हैं. Now, someone has to tell me the units. Now, assuming this is a balanced equation, tell me the units of Kc and tell me an expression for Kc of this equation. Now, this equation is balanced, by the way. Tell me Kc with units. And by the way, this is an MCQ, has been tested multiple times. Kc and its units for this equation. You have 30 seconds to write it down. Okay, just take 1 minute to write it down. Guys, I need an answer now.
Sir, won't it just be 1
Yes,
over
sir.
mole per dm cube?
Sorry.
1 over mole per dm cube.
Okay, and what's the expression for Kc?
C square into
Mhm.
d
C squared into A divided by A into
B cube. B raised power 3.
B cube. All right, good. And what's the unit?
Sir, 1 over mole per dm cube.
ठीक है,
Capital asymmetric.
मोल इनवर्स डीएम क्यूब. क्या चीज? कुछ पूछ रहे हैं मत? माइक आपका वो हो गया, म्यूट हो गया.
बता रहा था मैं.
नहीं समझ आई आपकी बात.
नो सर, मैं यूनिट बता रहा था.
अच्छा अच्छा, सही है. तो ये समझ आ गया ना यूनिट कैसे आया. ये आगे बढ़ते हैं. सो ठीक है, तो ये यूनिट की भी थोड़ी सी प्रैक्टिस हो गई. आगे बढ़ते हैं. अच्छा, सो नाउ before I move on to Le Chatelier's principle, let's do a few important example questions. And these example questions are actually tested. ठीक है, जो टेक्स्ट बुक में गिवन है ना यही पूछी जाती हैं. बाय द वे एग्जांपल क्वेश्चंस नहीं, एग्जांपल्स जो कि टेक्स्ट बुक में गिवन है ये पूछी जाती हैं. कुछ इंपॉर्टेंट इक्वेशंस है, उनके केसी बनाने आपको आने चाहिए. ठीक है, उनके सिनेरियोज दिए हुए होते हैं. नाउ दिस is ethanoic acid, जिसको acetic acid भी कहते हैं. This is an organic acid. It's a weak acid. If it reacts with ethanol, so acid alcohol reaction के result में you get an ester and water, right? This reaction is actually a reversible reaction. Formation of esters का जो reaction होता है जिसका esterification या condensation कहते हैं, it's a reversible reaction. ठीक है, and the conditions are concentrated acid and heating is required as well. Now इसकी अगर आप किसी की एक्सप्रेशन बनाएंगे तो कैसे बनाएंगे ये आपको पता होनी चाहिए. मैं इस एस्टर को यहाँ पर लिख लेते हैं. तो CH3COO C2H5 into concentration of water divided by concentration of the acid and concentration of the alcohol. ठीक है, ये केसी की एक्सप्रेशन हो गई. इसके यूनिट्स क्या होंगे? There are gonna be no units at all. क्यों? बिकॉज चारों के चारों यूनिट्स क्या हो गए, कैंसिल आउट हो जाएंगे यहाँ पर. ठीक है
Sir,
जी.
तो इसके अंदर H2O हम क्यों include करते हैं?
H2O हम क्यों इंक्लूड कर रहे हैं? इसलिए इंक्लूड कर रहे हैं बिकॉज दिस वाटर इज नॉट इन एक्सेस, दिस इज अ प्रोडक्ट, राइट.
So कौन से cases होते हैं जिसमें नहीं include करते हैं?
उस केस में नहीं करते जब वाटर इज यूज्ड एज अ सॉल्वेंट या वाटर इज इन अ लार्ज क्वांटिटी. इसमें वाटर इज इन अ वेरी लिमिटेड क्वांटिटी. गेट इट? इट्स अ प्रोडक्ट एंड इट्स लिमिटेड. तो इसलिए वी हैव टू इंक्लूड वाटर. बट इफ वाटर इज एक्सट्रीमली लार्ज, water is large, it's high, such that its change in concentration will not affect the concentration of water, such that the amount of water which is used in the reaction will not affect, will not change its concentration. So in that case, you don't need to include water. But in this case, you have to include water because this is just a limited amount of water which is produced in this reaction. ठीक है?
syllabus में और कौन से है? KSP है?
और कौन से क्या?
मतलब solubility product हम पढ़ते हैं कि नहीं?
अच्छा अच्छा, उसकी बात कर रहे हैं, कांस्टेंट्स की बात कर रहे हैं.
जी सर.
सॉल्युबिलिटी प्रोडक्ट बिल्कुल पढ़ते हैं, लेकिन वो यहाँ नहीं, वो दूसरे चैप्टर में पढ़ते हैं. एसिड बेसिस एंड सॉल्ट्स वाला चैप्टर.
और कोई कांस्टेंट्स पढ़ते हैं?
जी बिल्कुल हैं. केपी भी आएगा अभी थोड़ी देर में या फिर इसी चैप्टर में, मतलब आगे आएगा. ठीक है, और के ए और के बी भी आएंगे. ठीक है, और के पी सी भी आएगा. तो सारे कांस्टेंट्स हैं. इट्स अज्यूम नॉलेज. ठीक है. अच्छा, सो no units at all, and this is the expression of Kc for this इक्वेशन। अब यहाँ पर जो है ना इसके कुछ क्वेश्चंस आते हैं, उन्हें कहते हैं आइस क्वेश्चंस या आइस टेबल वाले क्वेश्चंस, या फिर वो अभी नहीं करते, चलो उनको इग्नोर कर लेते हैं यहाँ पर। एक और एग्जांपल है PCl5 वाली, PCl5 breaking down to give you PCl3 and chlorine। अब इसकी भी एक्सप्रेशन बनाना आपको आनी चाहिए। So Kc is gonna be concentration of PCl3 into concentration of chlorine divided by concentration of PCl5, and इसके यूनिट क्या होंगे, सिर्फ मोल पर डीएम क्यूब होंगे, बिकॉज मोल पर डीएम क्यूब से मोल पर डीएम क्यूब एक कैंसिल आउट हो जाएगा। आगे चलते हैं। Decomposition of N2O4. N2O4 is a gas. It decomposes to give you 2 moles of nitrogen dioxide. In this case, what will happen? What's the expression that you'll make? Kc is gonna be NO2's concentration squared divided by N2O4 concentration. And again, the unit is just mole per dm cube. Okay. Then अमोनिया की तो हम ऑलरेडी कर चुके हैं। अब एक और इक्विलिब्रियम कांस्टेंट आता है, उसे कहते हैं Kp। ठीक है, Kc के बाद आता है Kp। For now, there is a very important equation that I would want to give you. There's a relationship. Okay, let me just first tell you what Kp is. What was Kc? Kc was an equilibrium constant that told you about the position of equilibrium, correct?
Pressure constant.
G बिल्कुल pressure constant Kp, ठीक है। पहले Kc की अभी हमने बात की, it was the equilibrium constant of concentration, right? Reversible reaction में Kp is also an equilibrium constant, but this P over here represents pressure. So it's actually the equilibrium constant of pressure for a reversible reaction. And this is applicable only on gases, not on liquids or solids, ठीक है? Because gases have the greatest effect of pressure on them, right? Kp की भी expression बिल्कुल उसी तरह है, लेकिन instead of using concentrations, we are going to use partial pressures. Remember partial pressures that we did in gases? Partial pressure calculate कैसे होता है? Partial pressure, इसको P से represent किया जाता है, equals the mole fraction multiplied by total pressure. ये फॉर्मूला था पार्शियल प्रेशर के कैलकुलेशन का, ये भी याद करना है आपने, ठीक है। ये हम वैसे कर चुके हैं ऑलरेडी गैसेस में, ये बाद में देखेंगे इसको। अभी जो ज्यादा इंपॉर्टेंट चीज है वो है रिलेशनशिप बिटवीन Kp एंड Kc। Kp equals Kc multiplied by RT to the power of delta N. Now this is a very important relationship, and let me explain it. Now Kp is equal to Kc when Kc is being multiplied by RT to the power of delta N. Now what is delta N? So delta N is actually the moles of products minus reactants. Moles of gaseous products minus moles of reactants. ठीक है, this is delta N, change in moles. R is the gas constant, right? And T is the temperature in Kelvin. Now here, the question that comes is never about calculating Kp or Kc, rather it's about this finding out the relationship between Kp and Kc. Finding out if Kp equals Kc, Kp is being greater than Kc, it's less than Kc, or it's just unequal to Kc. Kp is not equal to Kc. Now these are the 4 options which are usually given, and you are asked to tell from a certain equation if Kp is greater than Kc or not. Now, so let's do an example over here. Nitrogen plus hydrogen forming ammonia, right? 2 moles of ammonia and 3 moles of this. Take it. Now, these are the gaseous reactants, correct? Now tell me what's going to be the value for delta N. How many moles of gas are there in the product side? 2 moles? What are the total number of moles on the reactant side? 4 moles, right? 3 plus 1, it's 4. So 2 minus 4 will give you -2. So delta N in this case is -2. What does -2 indicate? Kp equals Kc multiplied by RT to the power of -2. What does this tell you? Kp is greater or Kc is greater? This will tell you that Kc upon RT to the power of 2 equals Kp, right? And so Kc will actually equal Kp multiplied by RT squared. So बड़ा कौन सा हुआ? Kp हुआ, Kc हुआ इस केस में? बताएं guys.
Kc.
Kc या Kp? बताएं. Kc will be more than Kp. Good. सही है. ठीक है.
एक
This
सेकंड
case-
RT माइनस स्क्वायर को नीचे कर लिया. अच्छा फिर अपने नेवर Kp को साइड पे ले गए.
सही है. मैं दोबारा भी बता दूंगा लेकिन थोड़ी देर में रुका. देखिए ये RT का जो स्क्वायर्ड है ना, स्क्वायर्ड, ये जरूर कोई ना कोई नंबर होगा. ठीक है, आप क्योंकि स्क्वायर में आ गए. जब ये आप Kp से मल्टीप्लाई करोगे तब जाके Kc का आंसर आएगा, मतलब Kc Kp से बड़ा है. If we take another example, sulfur dioxide reacting with oxygen forming sulfur trioxide. In this case, what do you think? इसमें देखें प्रोडक्ट्स और रिएक्टेंट्स के मोल्स देख लो. प्रोडक्ट साइड पे 2 है, रिएक्टेंट साइड पे 3 है. तो अगेन डेल्टा एन क्या होगा? 2 minus 3, ओके, -1 होगा. अगर ये माइनस में आ गया है तो मतलब क्या हुआ? ऑब्वियसली Kc इज अगेन गोना बी ग्रेटर देन Kp, जस्ट लाइक द प्रीवियस वन. सही है. ये बात सबको समझ आ गई? अगर डेल्टा एन नेगेटिव है तो Kc विल बी मोर देन Kp. अगर डेल्टा एन पॉजिटिव निकला उस केस में Kp is going to be more than Kc. ठीक है? If this part is clear, please show me raise of hand. Oh, it's only me, Mishle now. Yes, Mishle. So is it clear?
Yes.
सही है. And by the way, ये important part था क्योंकि A levels में नहीं होता, ये equation नहीं होती, relationship between Kp and Kc. ठीक है, तो ये आपने अच्छे से करनी है. Applications of equilibrium constant तो इतना कुछ खास नहीं है. फिर उसके बाद conditions on position of equilibrium है, वो हम next class के लिए फिर छोड़ देते हैं. ठीक है, यहीं पर wind up कर लेते हैं. आपका अगर कोई question है तो you can ask Mishle.
Okay.